In chemical kinetics, we study how fast a reaction is happening, and the speed of the reaction is determined by how quickly the reactants are being converted to products. Now, when we have chemical equilibrium, with chemical equilibrium, what we're actually looking at it's how much product we're getting from a chemical equation. We have two groups where we can classify all reactions. Reactions that are irreversible. And by that, what I mean is that you have your reactants and the reactants are being converted to products. Now, the amount of product that you're getting from an irreversible reaction is going to be determined by the limiting reactant. Now, on the right side of the diagram, we have reversible reactions. For reversible reactions, what we have is a reaction where the reactants are being converted to products, but the products are also reacting to give back the reactants. So there are two reactions happening. You have the forward reaction, which is your reaction going in the forward directions. The reactants being converted to products. And we have the reverse reaction, which is the reaction where the products are actually reacting to give you back the reactants. So we represent a reversible reaction using a double arrow pointing towards the products and from the products towards the reactant. For the irreversible reactions, we use just one single arrow going in one direction, in the forward direction, because in the irreversible reactions, your products are not giving back the reactants. So when you have an irreversible reaction, the reaction will go to completion when your limiting reactant is consumed entirely. When you have a reversible reaction, since the reaction is going in both directions, in the forward and in the reverse direction, this reaction is going to stop at some point. And by stopping, it's not that everything is going to stop changing. What stopping means in this case is that your reaction is going to reach dynamic equilibrium. Dynamic equilibrium is what happens when the rate or the speed of your forward reaction is exactly the same as the rate or speed of your reverse reaction. So the reactants are being consumed at the same rate as your products are being consumed to give you back the reactants. That is what dynamic equilibrium is. And it's dynamic because that is constantly happening. So for the reversible reactions, the amount of product that it's being formed in the reaction is going to be determined by that dynamic equilibrium. Another thing about dynamic equilibrium does not mean that your concentrations are equal. It's not saying that the concentrations of your reactants are equal to the concentration of the products. What it means is that the speed of those two reactions, the forward and the reverse, are the same. Now, I have here at the top of the page a generic reaction. So in capital letters A, B, C, D, I'm representing the reactants and the products. Reactants A and B, the products C and D. And then I'm using the same letters but lowercase letters to represent the coefficients. So you have a coefficient A for your reactant A coefficient B for your reactant B, coefficient C for your reactant C and for your product C, and then coefficient D for the last product D. So we can write down an equilibrium constant expression. Now, the equilibrium constant, it's an actual number. It has a numerical value. The equilibrium constant, that value, it's giving us a lot of information. If you look at the equilibrium constant value, you can actually determine, okay, I have a lot of product when this reaction reaches a dynamic equilibrium. I have just a small amount of product. What can I do to increase or to make these reactants form more of that product that I want? So the equilibrium constant expression, we use capital letter K. It's just a ratio of concentrations. We have the concentrations of the products on the top part of my ratio, the concentrations of the reactants on the bottom part of my ratio. Now, those concentrations that we use for the equilibrium constant expression are concentrations at equilibrium. If you know how much you're using, how much is the concentration for the reactants that you're using, right? In the beginning, when you're starting a reaction, those concentrations are not at equilibrium. Those are initial concentrations. So when we look at an equilibrium constant value, that equilibrium constant value, it's being determined using concentrations at dynamic equilibrium. Now, when we're writing that equilibrium constant expression, you see, this is a common mistake where you write down the concentrations and you're adding them with a plus sign, similar to what you get to see in the chemical equation. Now, the equilibrium constant expression is the multiplication of your concentrations. So you have two products in this reaction, product C and product D. So in your equilibrium constant expression, we're writing concentration of your product C times concentration of product D. That's what goes on the top part of your ratio. Now your concentrations are raised to the power of the coefficient that you have. So I have my concentration for my product C, and I'm using brackets because brackets is what we use for molar concentration. So that concentration raised to C, lowercase c, because that's my coefficient for C in my chemical equation, times the concentration of my second product, which is D, in brackets and raised to the power of lowercase letter d, which is the coefficient that I have for D in my chemical equation. If you have three products, then you will have a third concentration multiplied in your equilibrium constant expression, raised to the power of the coefficient that you have in the chemical equation. Now, your products on the top part, and then on the bottom part of the equilibrium constant expression, we have concentration of your reactants A and B. They're raised to the power of the coefficients that you have in the chemical equation, and they're multiplied times each other. So since the equilibrium constant expression, it's a ratio, right? You're dividing what you have on the products by what you have on the reactants. You're going to have options. The value of the equilibrium constant can be greater than 1. And what that means is that the concentration, that overall concentration for your products when dynamic equilibrium is reached is going to be greater than the concentration that you have for the reactants, overall concentrations for your reactants. Now that makes sense because you have a chemical equation, right? Your reactants are being converted to product. The more product you have, what that means is that a lot of the reactants were converted to product. So you have a large amount of product, and what you have left is a small amount of the reactants. The second option is having a value for your equilibrium constant that is lesser than 1. That will happen when a small amount of the reactants is being converted to products. If a small amount of the reactants is being converted to products, you're going to have a small amount of product and a large amount of your reactants still left without forming the products. So this is a ratio, right? Your equilibrium constant value comes from a ratio. The larger the number that you have on the top part of your equilibrium constant expression, the smaller the number that you will have on the bottom part of that ratio, and that will give you a larger number. The larger number on the bottom part of your ratio means that you will have a smaller number on the top part, giving you a smaller value for that equilibrium constant. The last option is having a numerical value for your equilibrium constant that is equal to 1. A numerical value for your equilibrium constant equal to 1 does not mean that the concentrations are equal to each other. What that means is that the overall concentration that you have for the products, right? All of that concentration of the first product raised to the power of the coefficient times concentration of the second product raised to the power of your coefficient. That overall number will be the same as the overall number that you have for the reactants. When the equilibrium constant value is greater than 1, we say that the forward reaction is favored. What that means is that your forward reaction is the one that is giving you the products, right? So if you have a numerical value for K that is a large number, it means that you're getting a large amount of product. When you have a numerical value that is smaller than 1, it means that you have a lot of reactant presence giving you a small amount of product when that reaction reaches dynamic equilibrium. If you have a large amount of reactant and a small amount of product, the reaction that is being favored is the reverse reaction, the one that is going in the direction from the products towards the reactants. When the numerical value of K is equal to 1, then neither reaction is favored. So I have an example right there to calculate the value of K. So we're using the same chemical equation that we have on the top of the page, the generic one. I'm telling you, okay, assuming that all the coefficients in that equation are equal to 1, and I'm giving you concentrations. The concentrations that I'm giving you are concentrations at equilibrium. Remember, any numbers that you're plugging in an equilibrium constant expression are concentrations at equilibrium. If they are not concentrations at equilibrium, you cannot use those numbers in the equilibrium constant expression. So I'm giving you numbers. Concentration at equilibrium for A is equal to 1, for B it's equal to 2, your product C is equal to 3, and your product D is equal to 4. Assuming that all coefficients are equal to 1, calculate how much is the value of your equilibrium constant. Here we have some important information about the equilibrium constant. First thing is that there are different representations for an equilibrium constant. All of them are representing the same thing, the ratio between the concentration of your products during dynamic equilibrium over the concentration of your reactants. That is not changing. What is changing is the symbol that we use to represent those equilibrium constant. For example, you can see K, just K, that's equilibrium constant. You can see K, EQ, that's equilibrium constant. KC, usually this one represents equilibrium constant based on concentrations, but based on concentrations you can have just K, you can have KAQ, all of them are representing the same thing. Now we use some other notations to identify the equilibrium constant. For example, we have Ka. K is still the equilibrium constant, but now that A is what we use to represent an equilibrium constant for the dissociation of an acid. Kb is what we use to represent the equilibrium constant for the dissociation of a base. Kp when we have an equilibrium constant based on pressures. Instead of having concentrations, we have a numerical value for pressures. And then the last one, Ksp, it's an equilibrium constant that we use when what we're looking at is the dissociation of a solid in water or in a solution. But all of them are representing the same thing. Okay? Concentration of your products over the concentration of the reactants. Or if you have pressure, it will be pressure for the products over pressure for the reactants. When we have in a chemical reaction pure liquids or pure solids, those concentrations are not going to be part of the equilibrium constant expression. We include concentrations for gases. We include concentrations for aqueous substances. Aqueous substances are not the same as liquids. Liquids are pure substances like water, ethanol. Aqueous substances are substances that are being dissolved in water to form a solution. Another thing, the numerical value for the equilibrium constant is dependent on temperature. The numerical value for your equilibrium constant, if you have a large number, it means that the equilibrium, right, your you have two arrows, one going in the forward direction, one going in the reverse direction. That right there represents dynamic equilibrium. Okay? So that equilibrium is going to be moved to the right side where you have the products, because your equilibrium constant, that large numerical value, is telling you that when the reaction reaches equilibrium, you have a large amount of product and a small amount of reactants left. The opposite is also true, right? If you have a small numerical value for K, it means that your equilibrium position is going to be shifted towards the reactant, favoring the reverse reaction. This is related to your numerical value for K larger than 1, lesser than 1, equal to 1. Another thing, if the equilibrium constant, you have a numerical value for the equilibrium constant going in the forward direction. You calculate that numerical value for the forward direction. You have a number. The numerical value for the reverse reaction will be 1 divided by your value for the forward reaction, which means that it will be the reciprocal value of the forward reaction. So if you have a numerical value for the forward reaction, going from reactants towards products, that it's equal to 6, for example, and I'm going to put F for forward. The numerical value for the reverse reaction will be 1 divided by 6. So it will be given by 1 divided by 6, which is just the reciprocal value of 6. So you have two problems at the end. And in these two problems, what it's being asked, okay, you have a numerical value for K. First one, 1 times 10 to the minus 5. Second one, 156. Just looking at that number, write down if you have more products or more reactants when that equilibrium is happening. Now you have another problem. Right? The problem is giving you the value for the equilibrium constant for your forward reaction, and it's asking you to find out the value of the equilibrium constant for the reverse reaction. So you have a K forward equal to 10, and you're using that one to calculate the reverse reaction, that numerical value for K for the reverse reaction. And then you have a list of problems where you're writing down the equilibrium constant expression. So I'm going to do the first one and then you can solve the other three. So in the first reaction you have 2CO going to CO2, carbon dioxide plus carbon. Now the physical states are important. Remember that in your equilibrium constant expression, you're not writing down concentrations for solids or liquids. So the numerical value for your equilibrium constant, it's independent on the concentrations for pure solids or pure liquids. So I'm going to write down the first one and then you can do the other three. Concentration of the products CO2 raised to the power of the coefficient, there's no number, which means that is just 1. Now I'm not writing down C as a solid because that's a solid and it's not part of your equilibrium constant expression. So I'm done with the product side and now I'm moving towards the reactant. For the reactant, I just have one reactant, which is the carbon monoxide. So carbon monoxide, and the coefficient for that one is 2. So I'm writing 2 as the part, like it will be square, carbon monoxide, that concentration square, because the coefficient in your chemical reaction is 2. So that will be the equilibrium constant expression for the first one. Now for the second one, there's just one thing that I'm going to tell you and then you can write down your answers. When you have ions, right, ions are always in aqueous solutions. For you to get ions, you need to prepare a solution, right? You have a compound, you put that compound in water and then it will dissociate, giving you the ions. So even if they're not identified as AQ or aqueous, you need to know that they are aqueous.